All right, so today's lecture is going to be on water and its importance as a compound for sustaining and allowing life to exist. So, water is so amazing. It's one of the most amazing molecules that exists, and you really don't think about it that much because you drink it and you see it every day. But it's really kind of an amazing molecule and the way it behaves. So why is it amazing? So this is just some background information. 3/4 of the Earth is submerged in water, and because water exists, it's the main reason why Earth is habitable. There's so many creatures that live in the water. And not only that, if there are creatures that live on land, they've had to adapt evolutionarily. They've had to have adaptations to allow them to bring water on land with them. Even we do this. Our blood is an example of that. Our blood has to have water in it. If we don't have enough water, we will eventually die. All organisms, their goal is to get water somehow. So this is all well and good, right? But so why is water so amazing? What are the properties of it that make it so important for life? The main overarching property is its polarity. Now, a polar molecule, for those of you who haven't taken chemistry or AP chemistry, is a molecule that has an unequal charge distribution, usually because of electronegativity differences between the oxygen, which is more electronegative, and the hydrogen, which is more electropositive. And because of that, one of the most important things that we talk about in science, or one of the overarching themes that we see all the time, if you remember one thing, is that opposites attract. Positives attract to negatives. So because of that, water will stick to itself and it'll stick to other things. Those bonds that form between adjacent water molecules because of its differing polarity are called hydrogen bonds, as you can see down here. Okay, so electronegativity as a definition means it's a molecule, or it's a part of the molecule, or an element that craves electrons. And those electrons are going to buzz around that atom more often than they buzz around neighboring atoms. So oxygen is more electronegative and hydrogen is more electropositive. So the oxygen is going to buzz, or the electrons are going to buzz around the oxygen more frequently than they would buzz around the hydrogens. As a result, that gives that oxygen a partial negative charge and the hydrogen a partial positive charge. So this polarity that exists and these hydrogen bonds that form actually give water four main properties that you kind of want to understand. But polarity, remember, is the overarching thing that causes all of them. That is cohesion, adhesion, specific heat, the specific heat of water being high, the insulation effect of water, which means it's less dense as a solid than as a liquid, which is a kind of a rare thing in nature, and the fact that it is a universal solvent. All right, so first thing, cohesion and adhesion. So if I talked about a cohesive unit, that means you all stick together, right? So cohesion is water sticking to itself. And again, it's due to the hydrogen bonding and the unequal charge distribution. Adhesion, on the other hand, is water sticking to other stuff, which is also due to hydrogen bonding. So it can interact with the intermolecular forces on different types of molecules. An application of this in biology is how water gets up through the roots and through the trunks of trees and eventually out of the leaves through a process called transpiration. The water actually goes in these tiny little tubes that are in the tree, and it'll stick to the side of the tubes and stick to itself. As the water evaporates out of the leaves, or transpirates out of the leaves is the proper term to use, one of the molecules leaves and the whole chain gets drawn up down the whole entire tube, all the way down the tree, all the way to the roots. So as they evaporate, one comes out from the soil. So it actually creates a vacuum at the roots, sucking water in. Surface tension is also related to cohesion. That's if you've ever done a belly flop, that's why it hurts so bad, is that the hydrogen bonds are all sticking together. It's like you're hitting a solid surface until you break through the bonds. The larger the surface area of your body that is hitting the water, the more bonds you have to break, which is why if you do a belly flop, you're putting tons of surface surface area onto the water, and as a result it's super painful because you have to break more of those bonds. Whereas if you pencil dive in, there's less of that. But this is important for a lot of things because certain species live on top of the water and they use this characteristic of surface tension in order to survive and either get away from predator items or go and get prey themselves. Water also has a high specific heat. Now, what this means is it's basically a substance's ability to increase in temperature and how much energy it takes to increase that temperature. So some things have very low specific heat, meaning that they increase temperature very quickly with very little energy added. Metals are like that. If you've ever put a pot on the stove without any water in it, that pot heats up very quickly. But as soon as you put water in it, that water takes forever to heat up. That's because water has a high specific heat. So it takes lots of energy to increase the temperature of that water only a few degrees. And that's important for life because it allows life to kind of maintain homeostasis more easily. Temperature fluctuations don't happen that much. It's not that drastic. Like if it was 80 during the day and 50 at night, the water never really changes temperature. It usually stays at about 70-something degrees in that situation, regardless of what the temperature is at night. And if the temperature is fluctuated quickly in the water, organisms would have to use energy in order to mitigate those fluctuations. So the fact that it has a high specific heat and it doesn't change temperature very quickly is actually a benefit for life. Okay, so heat is also, as it says here, heat is absorbed when we break the hydrogen bonds, and heat would be released when hydrogen bonds would be forming. So another characteristic that isn't exactly specific heat, but is related, is evaporative cooling. The process of just turning water from a liquid into a vapor requires energy. Energy has to go into it. So as we sweat on our bodies, and we're forcing evaporation as maybe wind goes over us, that actually sucks heat out of our bodies and allows us to cool down. And this is one of the ways we try to maintain temperature homeostasis in our body. And as I said before, like on a windy day, that effect is enhanced. That's why it's not, like no one likes, even though it's 80 degrees, it's not fun to go swimming on an 80-degree day, right? If it's super windy, because that water evaporates really quickly off your skin, and as a result, you feel very cold. Water also tends to be less dense in the solid form, which is called the insulation effect. And it's called the insulation effect is because that we get that layer of solid ice on top, and then everything below it kind of stays at a temperature above freezing, which allows life to live and exist below that spot. Most solids, when you heat up molecules, right? Most things, as you heat them up, the molecules spread further and further apart, which should lower their density, right? Density is basically the measurement of how much matter is in something per unit area. So as you heat something up, the molecules spread apart, there's less stuff per unit area, so the density should decrease as you heat it up. And as you cool it down, it should increase. So in the solid form, you should have a more dense substance. But water doesn't do that. It goes from like gas, where the molecules are far apart, to liquid, where they're sloshing around, but they're still separated. And then what water does, instead of being a solid like this, it becomes a solid like this. So it's actually less dense than the liquid is. If water behaved the opposite way, on the top surface, water would solidify and then sink to the ground, and the whole entire ocean and everything would basically become a solid block of ice. Water is also the universal solvent because of its polarity. It likes to bond to other charged and other polar things. So if something has a charge to it, or if something is polar, water can dissolve it. A hydrophilic substance is something that water can dissolve. So that means it's also polar. Remember this, likes dissolve like. Polar substances like water can dissolve other polar things. Hydrophobic substances are nonpolar molecules, things that have pretty equal charge distribution throughout and are not charged. Things like fats, oils, those things are nonpolar. So, and water does not dissolve those. So when it's called the universal solvent, it doesn't mean it actually dissolves everything, but most things happen to be polar, so it dissolves most of those things. So you can see here the way water acts. Notice here's the chlorine ion up here, which is negatively charged, and the sodium ion here, this is actually salt, sodium chloride. Notice the negative parts are attracted to the positive sodium ion, and the positive ends of the molecule, the hydrogen ends, are faced towards the negative chlorine ion up here. In a dissolving situation, the thing that is doing the dissolving is the solvent. The thing that is being dissolved is the solute. You learned that in chemistry, but just as a quick refresher, right? So water actually interacts with proteins, and we're going to talk about this a lot. Proteins are the molecule that we focus on the most throughout the whole entire course, and you're going to see that as we progress through it. But water interacts with molecules, and the way water interacts with molecules is very important because it causes it to fold, the proteins to fold in very specific ways, and the shape of the protein always helps to determine its function. So, all right, the last thing I kind of want to talk about are acids and bases. So water actually does dissociate. It splits up into OH and H ions. Technically, though, if you have more hydrogen ions, those hydrogen ions will piggyback onto another water molecule and become H3O plus instead of just H plus. But for shortcut, you can just call it H plus. Okay. Acids tend to have more H plus than they have OH minus. Okay. If you have equal amounts of H plus and OH minus, what do you get? Well, you get water, pure water, and that's why. And it happens to be that the equal amounts are what determine the pH, and you'll see that in a second. So, whereas bases have more OH minus flowing around, they tend to accept protons, where acids tend to donate them. And a proton is just another term for an H plus molecule. So here's the pH scale. Things that have low pHs are more acidic, high pHs are more basic, neutral around 7. So that means these things have more H plus than OH minus, and these have more OH minus than H plus down here. Now changing of these pHs is very important for life because life likes to exist around a pretty neutral pH. Not perfectly neutral, but a pretty neutral pH. Usually most things live in slightly acidic conditions. But you can see here as pH fluctuates, even, you know, a tenfold difference in pH, which is technically only one, and we'll talk about this, 1 point difference in a pH value, can have pretty substantial effects on life. If we talk about a 100-fold or a 2-point swing on the pH scale, there's very significant effects on life. So living things like to be in a very narrow range of pHs, and we'll talk about later in the course and why that is, but it relates to how proteins fold. Here's showing you acid rain damage, and you can see here, notice Buffalo, New York, right there, has pretty acidic water, and that has to do with our the industrial characteristics of the Rust Belt areas. Notice Pittsburgh's pretty bad too. So we talked about H plus ions and concentrations and things like that, but what is pH? The actual calculation or the actual mathematical equation is it's the negative log of the concentration of the H plus ions. Now, the water dissociation constant, for those of you who took AP chemistry, is 1 times 10 to the negative 14th. So water dissociates into H plus or H3O plus and OH minus, which you can kind of see right here. So if you multiply those two concentrations together, they should equal 1 times 10 to the 14th. Now, if they're equal to each other, that means that the H plus concentration is 1 times 10 to the negative 7th, and the OH concentration is 1 times 10 to the negative 7th. They're equal. That's pure water, if you have equal H plus and OH minus. If you take the negative log of that, what do you get? The negative log of 1 times 10 to the negative 7th is 7, which is a neutral pH. Okay? So let's say your H3O plus concentration is 1 times 10 to the negative 3rd. That means your OH negative concentration needs to be 1 times 10 to the negative 11th because they have to equal negative 14 when you multiply them together. In that case, because the H3O plus concentration is 1 times 10 to the negative 3rd, if we plug that into our equation, the negative log of 1 times 10 to the negative 3rd is 3. So you'd have a pH of 3, which is acidic. Okay, so that's why we have a pH scale that runs from 0 to 14. It's based on these concentration of H3O or the H plus concentration. So the following are pH values. Cola is 2, orange juice 3, beer 4, coffee 5, human blood 7.4, which has the highest concentration of OH minus, which is the highest concentration of H plus. So the highest concentration of H plus is going to be the one with the lowest pH. So in this case, cola. the thing that has the lowest or the highest concentration of H minus would be the most basic thing. In this case, it would be human blood. Does that make sense? So human blood would have a higher concentration of OH minus, actually even than H plus, because it is, even though it's close to neutral at 7.4, it is slightly basic. All right, what buffers do, just so you know, they try to minimize changes in pH, massive fluctuations. For those of you who did titrations in chemistry, either in Regents or in AP, you know that there's that equilibrium point that shifts, and it's a massive shift that happens very quickly. Only a few drops can massively swing the pH. But if you add something like a buffer, which is, for the people who are in AP Chem, the conjugate base of the acid, usually that minimizes substantial changes in pH. Okay, so that's basically what a buffer is and what you want to know. It minimizes fluctuations, and because that's important, because if pH fluctuates too much, it affects life. Buffers are important for living things. In fact, we have buffers in our blood, and there are buffers in many aquatic systems. All right, so the pH of a solution is increased from 8 to 9. It means that because this is a logarithmic scale, that means one shift from one to the next is about a 10-fold difference. So it's H plus from a pH to 8 to 9 is going to be 10 times less, right? So that means the OH concentration is going to be 10 times greater in the case of this to this. So did we say that H plus is 10 times greater than it was? No, because it's 10 times less. The concentration of H plus is 100 times less? No, we said it's 10 times less. The concentration of OH minus is 10 times greater than it was? That's true. So that would be the answer. It's not 100 times less than what it was. Okay? Acid precipitation has lowered the pH of the lake to 4. What's the hydroxide ion concentration? Remember, so this represents a hydrogen ion concentration of 1 times 10 to the negative 4. So that means that the hydroxide concentration must be 1 times 10 to the negative 10th, which would be this answer right here. All right. So that is the lecture on water and pH. If you have any questions, feel free to come see me.